When you write Python scripts for security automation, whether for port scanning, HTTP analysis, report generation, or any other task you have already practiced, you are not just writing code that works. You are writing code that will run in sensitive environments, sometimes with elevated privileges, sometimes on production systems, and often against targets that hold real data. A script that works but is poorly secured can become a vulnerability in itself. This chapter covers 3 essential pillars of secure scripting: file permissions and execution rights, the shebang line, and secrets management. Each of these pillars directly affects whether your script can be safely deployed and trusted in a professional or regulated environment. File permissions and execution rights. On Linux and Unix-based systems, which are the dominant environments in cybersecurity and DevSecOps work, every file has an associated set of permissions. These permissions define who can read the file, who can write to it, and who can execute it. Understanding and applying the right permissions to your Python scripts is not optional. It is a fundamental security habit. Permissions are divided into 3 categories: the owner of the file, the group associated with the file, and all other users on the system. For each category, 3 types of access exist: read, R, write, W, and execute, X. These permissions are often represented as a sequence such as RWXR-XR or as an octal number such as 754. Let's take a concrete example. Suppose you have written a script called nmap_wrapper.py, similar to the mini project you completed earlier. If you run the command lsl nmap_wrapper.py and see RWXRWXRWX, that means anyone on the system can read, modify, and execute the script. This is dangerous for several reasons. Another user could modify the script to insert malicious code. A script that runs with elevated privileges could be hijacked if it is world writable. Sensitive logic or embedded information in the script becomes readable to all. The correct approach is to apply the principle of least privilege. Grant only the permissions that are strictly necessary for the script to function. For a script that only you should run, a permission of 700 RWX is appropriate. This means only the owner can read, write, and execute. If a group of authorized users also needs to run it but not modify it, 750 RWXRX is more appropriate. To change permissions, you use the chmod command. For example, chmod 700 nmap_wrapper.py grants read, write, and execute only to the owner. Chmod 750 nmap_wrapper.py grants read and execute to the group, nothing to others. Chmod 755 nmap_wrapper.py grants read and execute to everyone, but write only to the owner. For scripts that interact with sensitive data, collect scan results, or generate vulnerability reports, as you have done in recent activities, 700 or 750 are the safest choices. Ownership also matters. You should verify with LSL that the script is owned by the appropriate user and group. If a script is owned by root but is writable by a regular user, an attacker with access to that user account could modify the script and have it executed as root. Use the chown command to set ownership correctly. For example, chown analyst security nmap_wrapper.py sets the owner to the user analyst and the group to security. Another critical point: never make a script executable unless it is truly intended to be run directly. If a Python file is a module imported by another script, it should not have the execute bit set. This reduces the attack surface. Finally, be aware of the umesc setting on your system. The umesc determines the default permissions applied when new files are created. A umesc of 022 means new files are created with permissions 644 by default, readable by all, writable only by the owner. A more secure umesc of 077 means new files are created with permissions 600, readable and writable only by the owner. You can set the umesc in your shell configuration file or at the start of a script using Python's os module, os.umesc00077. The shebang line. The shebang line is the very first line of a script file. It starts with the 2 characters hash, called shebang or hashbang, followed by the absolute path to the interpreter that should be used to run the script. This line tells the operating system which program to use to execute the file when it is run directly from the command line. For Python scripts, the shebang line typically looks like one of these: #/user/bin/python3, #/user/bin/nem python3. The difference between these 2 forms is important. The first form hardcodes the absolute path to the Python 3 interpreter. This is predictable and explicit, but it assumes Python 3 is always located at /user/bin/python3, which may not be the case on all systems or in all virtual environments. The second form uses the nem command to search for Python 3 in the user's path environment variable, making the script more portable. However, using MVM introduces a subtle security risk. If an attacker can manipulate the path variable, they could redirect the script to a malicious interpreter. In security-sensitive contexts, especially when scripts run with elevated privileges or are placed in automated pipelines, the explicit absolute path form, #user/bin/python3, is generally preferred because it is not subject to path manipulation attacks. Always confirm the exact path on your target system with the command which python3. The shebang line must be the very first line of the file, with no blank lines or spaces before it. If it is not the first line, the operating system will not recognize it and will likely attempt to run the file as a shell script, causing errors or unexpected behavior. For the shebang to work, the script must also have the execute permission set, as explained above. Without the execute bit, the operating system ignores the shebang line and will not run the script directly. You must explicitly call the interpreter, python3 nmap_wrapper.py. A complete correct opening of a secure Python script for security automation would look like this. #user/bin/python3. #script, nmap_wrapper.py. #author, analyst. #description, runs nmap scans and captures XML output. This small header comment is not required but is a professional best practice. It helps anyone reviewing the script to understand its purpose and origin, which is especially useful when producing or auditing vulnerability reports. Secrets management. This is arguably the most critical section of this chapter, and one of the most common sources of security breaches in real-world environments. Secrets are any piece of sensitive information that your script uses: API keys, passwords, authentication tokens, private cryptographic keys, database credentials, or any other value that, if exposed, would allow unauthorized access to a system or service. The most dangerous habit, and unfortunately one of the most common, is hard-coding secrets directly in the source code. For example, API_key equals SK4F9A2C1D7E3B8A5F. DB_password equals S3cur3P at SS. This is extremely dangerous for the following reasons. If the script is shared, committed to a version control system such as Git, or simply read by another user with appropriate file permissions, the secret is immediately exposed. Even if the repository is later made private or the secret is removed, version control history retains every previous version. A secret committed even once is considered compromised. Automated scanning tools, used in DevSecOps pipelines, which you will encounter later in this course, specifically look for hard-coded credentials in source code. There are several correct approaches to managing secrets in Python scripts. Using environment variables is the most common and straightforward approach. Instead of hard-coding a value, you read it from the environment at runtime using Python's os module. Import os. API_key equals os.environ.get API_key if not API_key. Raise value error API_key environment variable is not set. The secret is set in the shell before running the script. Export API_key equals SK4F9A2C1D7E3B8A5F. The value never appears in the source code. This pattern is standard in continuous integration and continuous delivery pipelines, where secrets are injected as environment variables by the pipeline platform. Using a dedicated configuration file that is excluded from version control is another approach. You create a file such as config.ini or secrets.json, store your secrets there, and add this file to your git ignore so it is never committed. You then read the values in Python using the config parser or JSON modules. The important discipline here is to verify that the file is indeed excluded and to set strict file permissions, 600 or 700, on it. Using a secrets manager is the most robust approach for professional and production environments. Tools such as HashiCorp Vault, AWS Secrets Manager, or Azure Key Vault store secrets centrally, control access, rotate credentials automatically, and log every access. Your Python script authenticates to the secrets manager and retrieves the secret at runtime. This approach is beyond the scope of this chapter but is the industry standard in mature DevSecOps environments. The python.env library is a popular tool for development environments. It reads key value pairs from a file named env in the project directory and loads them as environment variables. This allows you to keep secrets in a local env file, which is excluded from version control, while using the same os.environ.get pattern in your code. Install it with pip install python.env and load it at the top of your script. From .env import load_.env. Import os. Load_.tmv API_key equals os.environ.get API_key. The env file should never be committed. Add it explicitly to gitignore hash, gitignore.env, secrets.json, config.ini. Regardless of the approach chosen, some additional rules always apply. Never print or log secret values, even for debugging. Use placeholders or masked values such as API key loaded, redacted. Never pass secrets as command line arguments if those arguments could be visible in process listings. The ps command on Linux shows all running processes and their arguments. Rotate secrets regularly and immediately after any suspected exposure. Keep the number of people and systems that have access to secrets as small as possible. Principle of least privilege applied to secrets. Putting IT all together. A secure Python script for security automation combines all three pillars. 1. It begins with a correct and explicit shebang line pointing to the Python 3 interpreter by absolute path taught 2. It is stored with strict file permissions, typically 700, so that only the authorized owner can read, modify, or execute it. It never contains hard-coded secrets. Instead, it reads sensitive values from environment variables, a protected configuration file, or a secrets manager. These practices are not bureaucratic formalities. They directly prevent real attack scenarios. A world-readable script exposes your logic and possibly your secrets. A world-writable script can be tampered with. A script with hard-coded credentials can be exploited the moment anyone gains access to the file or the version control repository. As you advance in this course toward more complex topics, automated vulnerability reports, web and application penetration testing, secure delivery chains, these habits will become second nature. The scripts you write are tools, and like any tool in a security professional's kit, they must be handled with care. A poorly secured script in the hands of an attacker is not a broken tool. It is a weapon turned against you.